Okay, so let's give you a quick preview of what we are going to talk about on centroid and moment of inertia. First of all, you will find these few charts hopeful, and these are centroids of some common shapes, and you can find it in chapter 5. And moment of inertia for some common shapes. Before we start, let me get my slide back, sorry. Let's talk about how we can find a centroid for using the method in integration. By definition, my centroid is defined as xdA over area A. My y is YdA area A. And you either define my dA as vertical bars, which is y dx, like so, or you can find my dA as x dy, which are horizontal bars, like so. Okay, so essentially what we're doing is that we're trying to break up the bar into little pieces and then trying to figure out what is the centroid of all the of each bar, and then we add them up, and we can then find where the centroid of the entire shape is. I should probably put a little bar there. So that means that the centroid of the bar, vertical bar, of the horizontal bar. So let's go ahead and do it one quick example. So let's say I want to find the centroid x bar. For what we have. Okay, let's see. Go ahead and erase this. I'm interested in finding the x bar, so we know that's the x of each shape, x bar of each shape, middle area integrated by the overall area. And first I need to decide which a do I take. Since I have x here, I am going to be using my definition of dA of that one. So I'm going to be rewriting it as x bar y dx over my area A. And how do we find my area A? My area A is very simple. My area A is simply, you can take either one of these definitions, but like I said, in this case, it might be easier if we simply take y dx. So it's simply integrate y dx. And this time, since y is equal to kx 1/3, I'm just going to plug it straight in. And my x is going to go from 0 to a, right? 0 to a right here. Therefore, if I go and integrate it, taking my constant out, 3/4 x to the 4th is a to 0. Therefore, I have 4/3 k, a to the 3/4. That's my area. Now, how do we find the x bar? Well, as you can see, I am now trying to sketch I already found my a, so I'm interested in worrying about the top part. What is my dA to be? It's the same thing, it's going to be y dx. And my a is simply 3/4 k, a to the 4/3. Okay? But what is this x bar dx? Let's see. So here is my thin strip, y dx, right? Where's the centroid of that in x? Well, it's just x. Therefore, this is x, y dx to the fourth k to the fourth third. And what we're doing is we're simply plugging in the y, kx to the 1/3 in here. My x's integration limit again will be from 0 to a, and I have 3/4 k, and you should be able to find the answer based on the integration. Okay? And can you now try to set up the y the same way? So y is going to be equal to the y bar dA. My area A is 3/4 a to the 4/3. And if I were set up my y in that way, I will need to set up my dA as x dy. Or actually, let's go ahead and set it up as y dx. In this particular case, I'm still looking at the same vertical bar, but here's my y, right? Can you see that my centroid lies right in the middle? So my centroid actually is equal to 1/2 of the y times the y I originally have. Remember, this is my dA. So I have my integration now with y squared. But we know what y is, so I'm going to substitute the y equation in here. I'm sorry, it's not ds, dx, right? Therefore, I can set it up as, I'm going to pull the 1/2 out, k squared x to the 2/3. Why am I doing that? This is the y squared, I'm squaring that. dx, and my area A. And then you can find out what your answer is. I'm not going to do the math, and I won't ask you to do this on the final, but this is something that you'll need to know. That's where the centroids come from. Now, for moment of inertia, it is a similar kind of thing, except that instead of integrating the centroid, we're now having a x squared and a y squared in the integration. And that is something I will talk about during the class period. So this is a quick preview of what we're going to talk about on Tuesday. Okay? Now for your homework, let's first talk about this particular problem. Let's say I have this funny looking shape and I'm interested to find where its centroid is at. Now how do I want to do that? Remember in the prior example, what we're doing is doing integration, right? But if I know instead of having something I need to integrate, I can look at it as this being three common shapes. One is you have this really large rectangle, this big one, which I'm going to call area 1. And then you have this smaller one, which I'm going to call area 2, and this even smaller one, which I'm going to call area 3. And by the same definition, if we say, I'm going to rewrite the definition again, if we say the centroid of the whole piece is equal to the centroid of each little piece, when I'm looking at a really, really small area, I can also then say centroid is equal to the small piece, but each area is now a definite area. So as you can see, what's the difference between the prior example and in this particular example is only the size of the area. In the prior slide, we're looking at a very small element, the differential element. But in this particular case, instead of looking at a very small element, the differential elements are now just simply 3 finite areas of these 3's. So I simply reduce my integral. Integral is its mathematical meaning is summation anyway. I now have a new definition or a redefinition of what my centroid is like. And the same thing with my y, okay? And these two are the two equations I will be using in finding the centroid. And that is something I would like to talk about in the next recording. So I'm going to pause this one right now and end the recording.